Hello, and welcome to Astronomy 100. In this video, we're going to wrap up our discussion of stellar evolution, and in particular, we're going to wrap up the idea of black holes. In the last video, we introduced the idea that following a supernova event, the collapse of the core, of course, which triggers the supernova to begin with, but the gravitational collapse of that core could turn the core into a number of objects. If the mass of the core is less than 1.4 solar masses, it's a white dwarf for all of eternity. If the mass is greater than 1.4 but less than 3 solar masses, it becomes a neutron star for all of eternity. But if the core is greater than 3 solar masses, gravity will just continue unabated and continue to collapse and shrink the object until it essentially shrinks it out of existence. And that becomes, of course, a black hole. Now, one key thing to remember from the last video is that a black hole, by definition, is an object whose gravity is so powerful that to escape the object, you have to travel faster than the speed of light. And since nothing in our universe, not even light, travels faster than the speed of light, then nothing escapes, not even light. So let's go ahead and get started into some of the other ideas that go with this. In the previous video, we talked about this idea called the escape velocity. And let me bring that back for you. The escape velocity of any gravitating body is 2gm over r, where g is the universal gravitational constant, m is the mass of the body you're trying to escape, r is the radius of the body you're trying to escape. And notice the inverse nature here. As r becomes smaller, v becomes larger. So a black hole is an object who is shrunk so small that the escape velocity is now greater than the speed of light. Now what I'm going to do is I'm going to introduce another equation, sort of an equation, I guess. With a black hole, the escape velocity is equal to or greater than the speed of light. If you remember, c is the symbol for the speed of light. So let's say we make the escape velocity the speed of light. So we're going to take the letter c and we're going to substitute it wherever the v is supposed to be. So we're going to make this up here into a c. Now what I want you to notice though is if we do a little bit of algebra, if we make this the letter c through substitution and then we solve for the letter r, we get this formula right here. Now the key thing to notice about this formula is r is the size of the event horizon. So remember, at the event horizon is where the speed of light becomes the critical escape velocity. So r is by definition how big the event horizon is. And I'll show you a picture about that in just a second. So 2gm over c squared equals r. Now let me bring up a diagram here. So the r is the distance between the singularity, the black hole itself, and the edge of the event horizon. And so remember, that's where the escape velocity becomes equal to the speed of light. Now we're going to give it a name, and the name actually comes from history. Back in the early part of the 20th century, we're talking like 1915, 1916, there was a physicist by the name of Carl Schwarzschild, where he was able to use the physics of the day to calculate the concept of this idea called an event horizon. So in his honor, we call the radius, the distance between the singularity to the edge of the event horizon, that is called the Schwarzschild radius. So for the rest of this video, if you hear me say Schwarzschild radius, what you should think about is the size of the event horizon surrounding a black hole. Now, what I want you to notice though, and this is what the statement down here is relating to, notice that 2 is a number that doesn't change. It's a constant. G, by definition, is a constant, the gravitational constant. C, the speed of light, is a constant. So notice on the right side of the equal sign that you have a constant, and a constant. The only variable is the m, and the m is the mass of the thing that became the black hole. So the mass of the remnant core that gravity collapsed into the black hole. Notice, because m is the only variable, the only thing that can change r is m. If m gets big, r gets big, and if m gets small, r gets small. It's a direct relationship. So what that means is the size of the event horizon, how far away from the singularity the event horizon is, depends only on the mass of the black hole. So if you have an object of greater mass become a black hole, its event horizon will be larger, or the distance from the black hole to the event horizon is larger. So the size of the event horizon scales with the mass of the black hole. Larger mass black holes have bigger event horizons. Now that's a critical idea that becomes a big part of the whole concept of black holes, and we'll return to that in just a bit. So the question is, how do we find something that seems to be almost impossible to find? Remember that a black hole is something that does not reflect any light. So by the very nature of a black hole, you can't simply shine light on it and be able to see it, because any light that the black hole receives, it keeps. The black hole itself does not make any light. So how do we find something that seems to be impossible to find because we can't see them? Well, this of course was a challenge. In the early part of the 20th century, when the idea of a black hole was suggested, of course one of the problems was, will we be able to ever find something like this? Here's an artist's impression of the concept of a black hole. Now you'll notice this says solitary stellar mass black hole. So what I mean by this is, imagine that we've had a star go supernova, leaving behind a black hole. So a stellar mass, meaning it came from a star. Now this black hole wandering through the galaxy is not something we'll ever be able to see. But because of the intense gravity associated with a black hole, and because of Einstein's special theory and general theories of relativity, what we know is that the intense gravitational forces of the black hole will actually bend and curve space-time. So the light of anything behind this black hole, this is just the Milky Way, way off in the distance, the light from the objects way off in the distance, the light will become distorted as it tries to go past the black hole. So the light's path will be distorted because of the gravity of the black hole. So a single solitary black hole, if we had the luck to find one, should have a distorted view of the objects behind it in its vicinity. The problem is these black holes, the event horizon of a star that has become a black hole is just a few miles across. So can you imagine trying to find something that's just 2 or 3 miles in size that might be 1,000 light years away? So realistically, finding a black hole that's a solitary black hole wandering through the galaxy is going to be just about impossible. But here is how we do find black holes. In the 1960s and 1970s, we started to discover that there were binary star systems in our galaxy that had something very peculiar about them. And in this example shown in this diagram here, is there were a few binary star systems where you'd have one very normal star orbiting around something that didn't seem to produce any visible light. In other words, you had an object that was orbiting around what seemed to be nothing. And to make matters more interesting is, in X-ray light, there seemed to be quite a bit of X-ray energy coming from the vicinity of the object that didn't seem to exist. So these were called X-ray binary systems, and what astronomers started to figure out is that what they were actually finding was a binary system where one of the stars became a black hole, and the other star is still a normal star that is still forced to orbit the black hole. Remember, the black hole still has mass and gravity. Now, what's the source of all this energy shooting above and below this black hole? Well, what we know is that the material that the companion, the black hole's companion, the material from that companion star is being pulled off of it. So the companion star has some of its gas being pulled off of it due to the black hole's gravity. And then that gas swirls around the black hole. And when it swirls around the black hole, that gas becomes superheated to incredibly high temperatures. And because of the very intense magnetic field surrounding the black hole, the energy that is coming from this heated gas, the X-ray energy, of course, is going to be focused into a beam that goes above and below it. So if here's the black hole, you get this beam of energy that goes off in one direction or another because of the physics of this scenario. And so what we were actually seeing was the X-ray energy coming from the black hole companion to a normal star in a binary system. And we have found many examples of binary star systems that seem to have black holes that are in orbit around them. So the idea is we don't actually see the black hole. We can't. But the black hole causes the material in the environment of this binary system to behave in a way that reveals its existence. So black holes are sort of like troublemakers. We don't see them, but we see the trouble that they cause. Now here's another example. We now know that there are very, very massive black holes that exist at the centers of many, many galaxies in our universe. The idea is very similar. What happens is there's an enormous amount of material that is being eaten by the black hole, swirling around the black hole, and then of course superheated to incredibly high temperatures. And then the magnetic field surrounding this environment focuses energy and focuses material into two beams of material that go from the top and the bottom of the very center of this galaxy. And so what we end up getting is galaxies with focused beams of energy and matter shooting from the north and south pole of these galaxies. And one very famous example of this is the galaxy called M87. And M87 is normally an elliptical galaxy. Here's the view of this galaxy in visible light. But the Hubble Space Telescope took a few images of higher detail of this galaxy, and here's what it found. So at the very center of M87, this giant elliptical galaxy, is an object that is gobbling up an enormous amount of material and then focusing a beam of energy and material away from it that is shooting out into intergalactic space. So this object is shooting a beam from its center out into the space between galaxies. And here's an even closer view of that. So when we zoom in with the Hubble Space Telescope even closer and closer to the actual black hole, this is the material surrounding the black hole, and then this is the beam of matter and energy that is being focused away from the black hole itself. So notice, we can't see the black hole, but what the black hole is doing at the center of this galaxy is causing the consequences of all the things happening around it. And this beam of energy and material is basically revealing the presence of the black hole that is at the center of the galaxy M87. Now this led astronomers of the 20th century to ask, what about the Milky Way? This is an image of our Milky Way galaxy, but it's not in visible light. This is an infrared image of our galaxy. So these are all the places in our galaxy that produce infrared light. And this right here is the very center of the Milky Way galaxy. The problem is we have a hard time seeing the center of the galaxy with normal visible light because there's lots of dust, there's lots of gas, and we can't see it very well. But in infrared light, we can actually see through the dust and see all the way down to the exact center of our galaxy. And with some years worth of studying and observing the stars at the center of this galaxy, an incredible set of data was produced. So let's start over here on the left. Now what I want you to notice on the left is these are all stars. Okay, each one of these dots is a star. This is not normal visible light. These are false color images, the data of these stars. At the very center of this frame is the exact center of the Milky Way galaxy. Now what I want you to notice is after years worth of observing, you'll notice they can record the movements of the stars at the center of our galaxy. And notice how all of the stars at the center of our galaxy are moving, but notice how they all seem to have orbits around something that is not producing any light. So there is a dark, no light producing, massive object at the center of our galaxy. It's influencing the movements of all the stars in its vicinity, but it does not produce any light whatsoever. And so the center of the galaxy now has a name. It's called Sagittarius A star. So Sagittarius A star. And by observing the movement of these stars and knowing the force of gravity, we can calculate that the black hole at the center of the Milky Way galaxy is 4.1 million solar masses. It's enormously massive, and the size of its event horizon, or its Schwarzschild radius, is 7.4 million miles. So what we now know is that the Milky Way galaxy also has a very, very massive, very large black hole at its center, and this seems to be something very common to most galaxies in our universe. Now, in future videos, we'll talk about what the consequences of having a very massive black hole at the center of our galaxy is all about, but we'll save that for then. I hope you'll join me.